Hello, everyone. Thanks for joining us for another installment of our AMS webinar series. This month, we're covering 5-axis machining, which is a very interesting topic, and I think you guys will find it very informing. My name is Don LaCourse. I'm a senior application engineer here with MecSoft, and I'm joined also by Joe Anand. Joe is MecSoft's product manager. And I'll be going over the presentation slides, and Joe will be handling the actual 5-axis demonstrations. Joe, we want to go to the next slide? Okay, a few housekeeping tips here. If you've been with us regularly, you know a lot of this already. If you have questions during the webinar, there's a window in your GoToWebinar dialog for entering questions. And you can enter questions at any time. I'll be monitoring the questions in the background, and I will bring them up during the webinar, and we'll see if we can't get them answered. If for some reason we run out of time and we can't get your questions answered, we'll make sure to contact you directly with the answers. Also, a recording of this webinar is being made as we speak, and we'll make this available to you in a couple of days after we clean it up and get it ready to publish. Okay, Joe? Now, our agenda today. Everything today is talking about 5-axis machining. So initially, we're going to start out by talking about the different coordinate systems in CAM, and also the multi-axis machine setup, which is a very important topic for setting up your CAM parts to work with your specific 5-axis machine. Next, we're going to be talking about the different types of control geometry that you will come into in 5-axis machining. Drive surfaces, drive curves, check surfaces, all of the geometry types we'll be covering today. Also, we're going to talk a little bit about 4-axis continuous machining methods, and then also 5-axis continuous machining methods. In our product in 5-axis, you can output in 4-axis mode, so that you might be wondering why we're talking about 4-axis continuous methods. Also, we'll be talking about how to machine a mesh in 5-axis, which the process and procedure is different for mesh geometry versus NURB surface geometry. And then finally, we're going to talk about machine tool simulations. We're not going to actually set one up, but we have one set up in one of our slides, and we're going to show you how that works. And then also, we're going to talk about post-processing in 5-axis mode. Now, what are the benefits of 5-axis? Why should you get a 5-axis configuration from MecSoft CAM? Well, the primary reason is that you can machine complex geometry that you may not be able to machine on your 3-axis machine. Okay, if you have areas of the part that you can only get to from a 5-axis orientation, then obviously you're going to want a 5-axis machine because you won't be able to cut those on a 3-axis machine. Also, using a 5-axis machine, you can increase your accuracy of your machining only because there's less setups. You don't have to move the part around. Like I mentioned in item 1, you can get at all of your orientations of your features of the part using 5-axis. And then also, cutting, there's a lot of advantages for your cutting tools. You can extend your tool life by having a constant chip load. By machining in 5-axis, you can access the features, and using your tool to access the features, you can set up a constant cutting condition. And then also, you can get a better finish by using shorter tools, less deflection on the tools by using a shorter tool, and reducing tool and machine vibration. Okay, Joe? Now, the first thing we want to talk about is the different coordinate systems in a 5-axis machine. And what you see here on the left, you have a typical 3-axis setup where you have X, Y, and Z being the three primary axes and 3 axis. In the middle, you have a 4-axis setup. In addition to the 3 axes, you have the additional 4th axis rotation axis. And then on the right, you see a typical 5-axis setup. In the image that you see on the right, we're showing a head-head configuration where the 4th and 5th axis reside in the head of the machine tool. Now, when you get to 5-axis, there's 3 different configurations of 5-axis that you can set up your machine for. And all of them relates to where the axes are located on your particular machine. So on the left, we have a typical head-head configuration where the 4th and 5th axis are located in the head of the machine. And then in the middle, the table head configuration, you have the 4th axis on the table and the 5th axis on the head. And then on the right, you have a table-table configuration where both the 4th and the 5th axis reside on the table, and the spindle of the machine is doing the cutting. Now, this slide is actually relatively important, and Joe's going to go over a little bit more detail in an actual part. But on a 5-axis machine, you need to pay attention to what the gauge length is on your 5-axis head. And if you look at the illustration there on the right, you'll see that the gauge length is measured from the face of the spindle to the rotary axis on the head. So that's the gauge length that you may need to enter in your CAM file in order to get your 5-axis machine tool set up running correctly. Next slide, Joe. Okay, we have this slide here just so you know that you can run 5-axis in an indexed orientation, meaning that you can index your 5-axis machine to access any side of the part that you can get to in a 5-axis setup. And in this example, we have this part being machined from 3 sides, the right, the left, and the top. And there's a example machining job there in the middle where you can index your 5-axis machine at each one of these setups, lock it in place, and perform 2- and 3-axis machining operations. Okay. Now, in this example, we've got a number of examples in these slides we're going to show you, and that illustrates some of the key features. Now, you can perform 5-axis continuous flow curve machining in 4-axis mode. And we mentioned this earlier about using a 4-axis. Why were we talking about 4-axis? Well, in the example you see here on the right, you have a 4-axis part, but you have a surface that you can use 5-axis continual flow curve machining and output that in 4-axis mode. And then also you can use 5-axis continuous machining to machine complex injection mold blocks, core molds, cavity molds. In this example, we have a core mold that we're using 5-axis continuous between 2 curves machining, 5-axis continuous swarf machining, and then also a 3-axis offset pocket machining. And then the machining job in the middle illustrates how the mold machining operations are set up. Now, next we have a rotary instance, 4th-axis rotary instance example, where you can combine 5-axis machining with your rotary axis. So in the example on the right, you see we use continuous swarf machining, continuous surface machining, continuous curve projection machining. These are all to machine one instance of the rotary blade that you see. And then also you can implement your 4th-axis rotary instance to rotate that and then perform those 5-axis operations on each of the blades in the setup. Now we're going to talk about how to machine meshes and 5-axis. Mesh geometry can be relatively complex, and many of the mesh parts that you may have to machine can only be machined in 4 or 5-axis mode, just simply because of the complexity of the geometry. So you can set up a mesh to machine in 5-axis using 5-axis continuous methods. Next slide, Joe. And finally, we're going to talk about how you can set up for advanced machine tool simulation. In this example, we're simulating our mold example and on a 5-axis machine, as you can see here on the right. Just you want to watch that, okay? So also, if you need more information about anything that we talk about, obviously, you can give us a call or put a question in the question box and we'll get it answered for you. Okay, now we're going to move on to our demonstration portion. Joe is going to be handling that, and I'll be monitoring questions in the background. So please ask us questions and we'll get them answered during the course of the demonstration. Joe?
Thank you, Don. Welcome, everybody. So we are here with the 5-axis configuration demonstration portion of our webinar. And one thing I should mention is that all the functionality that you're going to see today is available in our what we call the premium configuration. So you would need the premium configuration in order for you to actually run all these Toolpath methods that I'm going to be showing. So let me talk very briefly about the different methods that we have. So if you do have the premium configuration, the browser, the machining browser is going to show up like that. And then you're going to have a 5-axis machining method drop down here. And the different methods that we have available in 5-axis are curve projection. It's very similar to 3-axis curve projection, except that you can take a curve and project it on a 5-axis mode. With normal surface normals acting to drive your machine tool angles. Flow curve is another type of machining where you actually select a curve and you allow it to walk along a surface or multiple surfaces and machine it in that fashion. Very similar to that is between two curves. For those of you who have the Pro configuration, you might be familiar with this, where you have take two curves, but this is on top of a surface or multiple surfaces, and this will basically morph between those two curves and create a cut pattern for you to machine in the particular geometry that you have selected. Drive curve, this is also another interesting method where when you have very complex geometry and very tight geometries where you can't really get in very easily, you can control the tool axis using this drive curve methods. Surface normal method is very similar to a parallel machining in 3-axis. Obviously, you're doing it in 5-axis mode here. It's a little bit more complex in terms of the computations and setups, but the principle is pretty much the same. And then we finally have the Swarf Machining method, which is unique to 5-axis. We're actually cutting with the side of the tool, typically in 3-axis mode, or for even in 4-axis, and many 4-axis methods, you're going to be cutting with the bottom of the tool or the sides of the tool, or rather the cutting portion in case of a ball mill. But in Swarf, you're actually cutting with the side of the tool. You're driving the side of the tool along a wall to machine it. So these are the different types of methods that we have available in the pre-configuration. And as Don mentioned, you're not restricted just to using these methods in 5-axis mode. You can actually use them on your 4-axis machine. The advantages that you get with the pre or premium configuration is that you have many more Toolpath methods to control your cutting process and thereby, machining different classes of parts that way. Okay, so that's a quick rundown of the different methods. I'll be going over and showing you different Toolpath meths is on different part files. Some of the things that Don mentioned in his slide. Before we run out of time, I hope we'll have enough time to show some of the complex features that we have. But before we get started, let me talk about the coordinate systems in CAM. This is very important to understand before we delve into the actual machining parts. And for those of you who are interested, deeper and a more thorough explanation of the coordinate systems, we did a webinar last month on index coordinates or index machining, and we went through a detailed explanation of the coordinate systems. But I'll briefly summarize it here so we understand what we're talking about in terms of the coordinate system definitions. Okay, so from our CAM system perspective, there's when you bring in a part file, let's say a very simple part file like this that I'm showing, it's just a rectangular block. This is in a Rhino environment, design environment. And Rhino design environment typically has these, if you look down at the bottom here, we'll have the XYZ icons. So that is what you can consider a design coordinate system or the world coordinate system. As far as the designer is concerned, that's the world that he's working with. So that's why it's called the world coordinate system. So once that design comes to the manufacturing side of things, the machinists that we are, those of who are machinists here, we'll look at it a little bit differently. We're looking at it from a machine viewpoint. And in most cases, the machine coordinate system, or the way the machine is set up, the X and the Y and the Z axes of the machines, will coincide with the design coordinate system. So here I show you the axes here, the world coordinate axes that our CAM system is displaying. And as you can see, it's parallel to the design system. So everything is fine and good here. In most CAD systems, this is the case. The world coordinate system coincides with the machine coordinate system. And so you don't have to do a lot of mental gymnastics to figure out where you're machining. But there are, in parametric systems like SolidWorks, they have chosen to take the sketch plane, the default sketch plane in SolidWorks is the XZ plane. And so the default coordinate system is not the typical machine coordinate system. So, and also the added complexity in a system like SolidWorks where you cannot actually transform the geometry once you have designed it. So we'll have to introduce a new transformation between the coordinate system, the design coordinate system, or the world coordinate system and the machine coordinate system. But in this case, in Rhino, everything is fine. So, and then we also have the setup. The setup basically defines additional coordinate systems that allow you to machine parts from different orientations. So the setup one that I have on the left here is basically the same as the coordinate system as the world coordinate system. And then you can, in addition to that, you can have a work zero, which basically moves the coordinate system up to a different point. You're not orienting the coordinate system any differently by using a work zero. All you're doing is transforming it. So it is moving it to a different location. And then you could also define a different setup here, where you can see the Z-axis is actually pointing, or the tool axis is pointing in that direction. What was previously the Y, or the Y axis in the world coordinate system. And then you can also define a work zero in this particular setup. So as you can see, this is my Z-axis for this new coordinate system, or the new setup coordinate system. And that's my work zero. That's where I'm going to be touching off the tool when I'm machining from that direction. So that's a quick synopsis of the coordinate systems that we have in CAM. Okay, let's jump into some of the details of 5-axis machining. The first thing you ought to do when you are looking at the 5-axis machine or machining is define your machine tool. This is the most important thing in 5-axis to get this right. So this is our dialogue for defining the machine tool. For those of you who worked with 3-axis, this is very simple. All you do is pick the 3-axis. You're not really concerned about any of the other things. But in the case of 5-axis, you select the 5-axis type of machine, and then you have to define the configuration of the machine. Don talked about the 3 different machine configurations that we support, and those are head, which means the 4th and the 5th axes reside on the head. and then the table head, which means the fourth resides on the table and the fifth on the head, or you can think of it the other way. Fourth is on the head and fifth is on the table. And then table, both of the rotary axes are on the tables. So we have different classes of machines. And your machine tool manufacturer and you will let you know which type of machine you have. And it's pretty obvious when you look at the machine. Okay, and then we also have a tool change point that you can define that basically defines where, if you have a tool change and if you want the spindle to retract to that point, you can specify that point here. And then I'll come to this checkbox here, output all coordinates and local coordinate systems in a minute. Then the min-max, you're familiar with that, the translation limits of the machine tool. And then here in the two groups here, we have the fourth axis, which defines the primary axis, the fourth axis. And you can specify the rotary center. As you can see, when you select the dark or the thick red arrow defines your rotary axis. And you can select, right now, when you select head, you only have these two combinations, either the plus Z or the minus Z. Those are the only two things you can select. And then the fifth axis, you can select either the X, positive Y, or negative Y. And then obviously, since you can't have both of these axes on the same coordinate axis, so this is grayed out. Okay, let's talk about, and then also one important thing that we need to specify is also the axis limit. Some of your machine tools might have some axis limits because of they cannot turn more than 360 degrees, for instance. Some of them who are running on rack and pinion systems could have no limit. But you can define the limits on your machine tool here by specifying this. I'll say 0 to 360 in this particular case. Okay, let's talk about now the output of the coordinate systems, output of the coordinate positions and the angles. So this is something Don alluded to, and I want to delve into it a little bit deeper here. We see three classes of machines out there. Some of the older controllers, which we consider do not have integrated controls, which means they do not understand how all of these three or five axes interact. So to handle those cases, and especially this applies only for head configurations. If you have either a head or a table head configuration, you will have to define something called the gauge length, which is basically the distance between the pivot point and the tool tip. The reason we need that, I'm going to talk about that a little bit deeper here. Okay, so the gauge length defines that length, and you saw the graphic that Don showed. So let me talk about that here. Let's take a simple case where you have I have a head machine here. I have a display of a head machine. So this is a tool pivot point. This is what Don mentioned in a slide. So we have a 5-axis machine configuration kind of schematically shown here. We have a C-axis. That's basically the C-axis rotates about this. The Z-axis here, the blue line. I'm not sure if you can see it. And then the secondary axis is the B-axis, which rotates about the Y-axis here. And this is where that point is where the tool is actually pivoting about. So as the B-axis rotates, the tool is pivoting about that point. And then this is where you're touching off. This point is where you're touching off. Okay, so if this is your machine configuration, and then you told the machine to move to a certain point. Let's say you told the machine to move to this point. The machine will do it fine, no problem, because it knows its X, Y, Z coordinate system change. So it's just going to take that and do a translation over to here. So you can really think of it, the machine is actually moving this pivot point, and it knows this offset because you've touched it off. You know the tool offset along the Z direction, and so it knows this point, where to move that point. Now in 5-axis mode, it's a little bit more complicated. So let's talk about a 5-axis position. Let's say that's where you have the point that you want to go, but at the same time, you want the rotary axis to be, maybe rotated 90 degrees on the C-axis and then another 90 degrees on the B-axis to get you that configuration so you can attack that other side come from the other side and machine. So in the case of these old controllers, they are not integrated in the sense that they don't know what the rotary axes and the XYZ motors are doing. They're independent axes. So if you told the machine tool to go to this point, what it's going to do is it's going to do this, because it does not know that the B and the C have rotated. Obviously, you don't want that to happen in 5-axis mode. So our CAM system automatically computes the offsets correctly for you. I don't want to get into the math too much. I don't want to lose you too much, but if you're interested, you can call us and we can give you a position paper on how that's done. So basically, what our CAM system really does is it does a math to backs off by the tool axis vector to that point, and then also uses the tool offset, the Z offset along the Z axis, and this is the point that it actually outputs. So if you look at the G code, you'll actually see this point being output rather than this point. But since the rotations are taken place, the machine tool works as you commanded it to work. So this is the one class of machines that we handle. And if your machine is something that uses an older controller that does not do the math in the controls, we do it for you. And the math, the way you define it is by defining the gauge length here. Okay, and the second class of machines, which we see more often, which is kind of like the mid-range set of machines, those actually can handle the kinematic, the math in the controller itself. In those cases, we leave that gauge length to be 0. If you leave it as 0, we know that the machine tool is handling the mathematics behind the rotations. So we will actually output this point to the control rather than this transform point. And then finally, we have these high-end sophisticated machines that actually can do what's known as TCP programming or tool center programming or rotated plane programming. There's different terminology for that. And if you have one of those kinds of machines, you can actually output everything in the rotated coordinate system or the local coordinate system. In this case, we're talking about setup 2. Let's say you rotated your coordinate system to setup 2. Now, all you have to do is you don't even need to output these points in a world coordinate system. You're actually outputting it in this coordinates frame or this coordinate system, if you will. It's a little bit complicated. It'll all be clear when you do have questions, you can always talk to us about it, and we set it up all in the post processor, so you don't have to worry about it. I just wanted to give you a quick rundown of where things are in terms of the programming part. So it's very important to understand what class of machines that you have, and also set up the output coordinates the way you want it to be. And your controller manufacturer can help you with that when you set up your machine. Okay, I think we spent a lot of time on that. We got about 30 minutes left. Let me cancel this out. Okay, so let's dive into the actual control geometry part of it. So I'm going to load a file here. Okay, this is something that I've created before. So a part that could be very well be manufactured in 3-axis, but obviously due to the nature of the surfaces here, it lends itself to 5-axis very nicely. So a little bit about the way we use geometry in 5-axis mode. For those of you who are familiar with the 3-axis parts, what we do in 3-axis mode is everything that you see is what we machine. In 5-axis, it's a little bit different. We don't do it that way. We actually allow you to select the surfaces that you want. And then let me talk about that. So in this particular case, look at the control geometry. I'm doing what's known as, actually, let me start out with a brand new between two curves machining. I'll show you how the programming is actually done. So I'm going to use the between two curves machining here. So the first thing you do, you define these two sets of geometry. One is called the drive surface, and then the drive curves. The drive surface in 5-axis mode, as compared to the 3-axis mode, there are two things associated with the cut pattern. In 3-axis, when you said parallel finishing, you would say basically take parallel planes along the X or the Y axis or any angle axis, and then basically slice the model, and then wherever this model is sliced is where you're cutting. You can think of it that way. But in 5-axis mode, apart from the X, Y, Z coordinates that we obtain from slicing, we also have the surface normals we use to actually position the tool along that surface normal. And then obviously there are some additional controls you can use to control the angles and the axes of the tool. To define that, you have to have a surface. So the surface basically gives us not only the coordinate points, X, Y, Z points to position the tool to, but it also gives us the tool axis vectors to use to position the tool. So I'm going to select the surface that I want to machine. So that would be one surface. I'm going to select the other surface, and then I'm going to select that surface as well. So those are, or there's one other surface down at the bottom. So I want to machine all of these surfaces. Okay, once I do that, and then the other important thing is to, in surface normal or surface machining, is you have to define the tool axes, the surface normal, and make sure that they're pointing the correct way. As you can see, the surface normals are all pointing down. So I'm just going to do flip all normals, which allow them to point upwards. And this basically defines your tool axis vectors to say I'm coming from the top to machine rather than coming from the bottom to machine. That's what it does. Okay. All right, and then I've created I've selected these two curves as flow curves machinings. Okay, let's talk about the tool. Very similar tooling is exactly similar to the 3-axis methods that you have. And you can select the ball, flat, corner radius mills, taper with corners. Those are the types of machine tools, cutting tools that you can use in 5-axis. So, and then feeds and speeds, it's very similar to 3-axis. We don't need too many explanations here. Let's talk about clearance plane. The clearance plane is a little bit different in 5-axis. In 3-axis, we just have a planar clearance plane on top of the part like so. But in 5-axis, we have additional controls. You can have a spherical clearance plane for parts that you can approach it from any different direction. And you can also have a cylindrical clearance plane. For instance, if you had a 4-axis type of part, you would use this kind of clearance geometry. I shouldn't call it plane, it's just clearance geometry. But in this particular case, I'm just going to use a flat plane for the clearance geometry. Let's talk a little bit about cut parameters. Cut parameters, you can specify whether you want the output to be in 5-axis mode or in 4-axis mode. We talked a little bit about this. This is only available in the premium configuration that you can drive or create the toolpaths either in 5-axis mode or in 4-axis mode, depending on what your machine tool is capable of. And then cut tolerance, you're familiar with that. Max angle change, these are things that we use to control the accuracy of the toolpath. And then the cut traversal, whether you want the zigzag pattern or the zig pattern. Step over, this is the distance between two paths, very similar to 3-axis. Tool axis control, we can say you want it to be fixed axis. You might want to do it in 3-axis mode, for instance. If you want to do surface machining in 3-axis mode, you can say fixed axis. Select fixed axis and lock the axis to the Z-axis and drive it. You can also specify, otherwise I'm going to leave it unchecked, which means it's going to use the surface normals and do true 5-axis mode. And I'm going to select the 5-axis machine here, configuration here. And then also, these are two important things. You can you can modify the tool axes by specifying a lead or a lag angle. A lead angle is an angle that tilts the tool in the direction of the cut. So if you set a lead angle of 10 degrees, it's going to take the surface normal and tilt it along the cut direction by 10 degrees. And a lag is basically a negative angle. And a tilt angle is basically normal to that cut direction. So we can get into that later. And tooltip control, this allows you to move the tooltip in or outwards. If you wanted to do roughing, you can do that with this methods. Cut levels, you can also specify cut levels, similar to Z-axis control or multiple cut levels. Entry exits, I don't want to get too much into the details. Your eyes might glaze over. And let's talk about Gout check. Let me generate this toolpath first. So it's going to run. Okay, there's my toolpath. As you can see, let me go in and change the step over direction. Please type in your questions if you have any questions, and I might be giving you a lot of information here. So I want you to make this as interactive as possible. So I changed the step over direction, step over control amount, which basically controls the distance between two successive cuts. And as you can see, it's a really nice toolpath. But as you can see, these gray surfaces down here are being machined, which we don't want. And the reason this little boss that's sticking out is not machined is because it's not part of the control geometry. I didn't select that as the drive geometry, so it's fine. So how do we avoid these? So that's the other set of control geometry that we have in 5-axis, which we call Gout check geometry or check geometry. So basically we can tell the system that, hey, I want to machine these surfaces, but I want to avoid these surfaces. So basically check against them. So I'm going to add these surfaces as my check surface. I'm going to select them. If it's a poly surface, it's probably easier to select the. Okay, let me select that. Let me, for the sake of, I don't want to select that for now to keep it quick. And then we also have a gout check strategy. So we can leave out the cutting gouging points. Or we can retract along the tool axis and by a clearance and not machine those surfaces. Let me do this first. If I do that, it's still machining. As you can see, it's avoiding that gout check geometry that I selected. So that's very similar to the way it handles this boss, because I did not select it in the surface geometry to machine. But here we're actually specifying this to be avoided. And the other thing I can do is, instead of doing that, if you don't like the way it picks up over that control geometry, I can go back in there and change my gout check strategy to actually retract along the tool axis. That might give you a better tool path and a lot less vibrations in the tool. So here, basically, we're moving up above that surface and not and avoiding it completely. So those are the two types of, or three types of control geometry, if you will, that we have in 5-axis mode. A little bit different than in 3-axis. So we have the drive surface. Drive surfaces define your cut pattern, not only your cut pattern, but also your tool axis vectors by taking the surface normals from the drive surface. And then you have drive curves, which actually, depending on the way you select it, they define the cut pattern on the tool surface, on the drive surfaces that you've selected. And finally, we have the gout check surfaces or check surfaces that are the surfaces that you want to avoid. So these are the three types of control geometry that we have in 5-axis mode. It's a little bit different than the 3-axis mode. That's why we spent a lot of time trying to make that distinction. Okay, any questions at this point? Don, anything that I need to show, answer?
No, we're all set for now.
Okay, very good. Okay, let's move on. I want to show you this part where we're actually machining a 4-axis part using the premium configuration. Okay, this is a 4-axis part. You could possibly do it in 4-axis, but the complicating factor here is that that surface, that cam surface, if you will, that is not readily machined using our 4-axis methods. So the way we have chosen to machine, I'll go through this. We've already machined it. I don't want to go into that in too much detail, but I'll just show you the toolpaths and how they work. One other note that I should make is 5-axis. When we talk about 5-axis machining, you're always going to be using that in combination with 3-axis methods, because there's a lot of power in locking the tool axis and machining with the lock tool axis. And there's a lot of toolpath methods we have in 3-axis that you can leverage. And so seldom will you machine everything using 5-axis. So there's always a combination. So here, what we have done is we have done a horizontal roughing. Let me run the simulation real quick. I want to simulate to end. So turn off the toolpath. So we've done that. And then we flipped it over. Since it's a rotary, we can flip it over very easily and then machine the bottom portion. And notice again, this is done using the 3-axis methods, and of course, using the index 3-axis methods. And then for the top part, for that little index part that you saw, we machined using, again, 3-axis. And then we did a chamfer to remove that chamfer operation. So all of this is 3-axis methods. So until here, we have 3-axis method. Now when to get to the rotary part, we're actually jumping into some 4-axis methods as well. So we're using quite a bit of combination of 4-axis. We just clean that up. Let me show you the toolpath. So we use the 4-axis face-off operation, if you will. And then we also use 4-axis engraving operation to actually clean up the sides to get that like that. Okay, and now just to get to I wanted to show you the difference between our 4-axis methods. We do have something called 4-axis drive surface machining that allows you to do machine something like that. But this is the only cut pattern you're going to be getting when you use that. As you can see, there's a lot of retracts. And the reason that happens is because it's checking against these. We machine everything we see in 4-axis. So it's actually checking against these geometries and picking up because of the gouges that are happening. But in the premium method, we have this flow curve machining that gives you a really nice toolpath, as you can see. It's a really nice pocketing type of toolpath, flowing about that surface and very nicely cleaning the corners and things like that. Let me run the simulation. Start the simulation. So, I mean, obviously, where the tool is not going like that, it's the machine tool. And run to end. Okay, there you go. So that's a very nice toolpath. And here we've used the 4-axis mode in the premium configuration to actually machine it. I'll show you the parameters real quickly. We used the 4-axis configuration and we used the drive curve method, single drive curve. We used the entire set of curves as a single drive curve, not necessarily a contiguous curve, but the system actually combines all of those curves to a single curve. So that shows you an example of where we can use a 5-axis method to actually machine a 4-axis part. Okay, let me show you another part example. This is an interesting one. It's a mold example. This is actually a quite complex part. You can machine this using 3-axis. You can see very nice surfaces, flowing surfaces. You can spend a lot of time using a small ball mill and trying to finish a lot of those fine surfaces. But we can show you the power of the 5-axis methods. So here, we did a horizontal roughing just like we would do on a. I think I can run the simulation very quickly. We have some time. Let me go to simulation, simulate to end. Let's turn on the toolpath. So that's my horizontal finishing. And then we did a facing operation to clean up the top surface here. Okay, and then we used a 5-axis, very similar between two curves machining. So we selected this surface, this set of surfaces, and we selected these two curves to drive the cutter. So let me simulate that. So basically, as you can see, the surface finish is really nice. You're not going to get this kind of surface finish in 3-axis mode. You have to use a very fine step over and a ball and mill and spend a lot of time to machine that surface in 3-axis mode. And then the next thing we did was we did a swarf machining. So basically we selected this wall as the wall surface, and this is as our floor geometry, and basically drove that wall. So let me run that simulation. So we're driving that wall, and it cleaned that wall up really nicely, as you can see. That's the swarf machining. And then the next thing we did was we wanted to machine this bottom surface, and we did a very similar between two curves. We selected this curve and said drive that surface and machine it. And obviously we were gouge checking against the rest of the geometry, so it's not gouging the rest of the geometry. So let's machine that. And then this one was actually a 3-axis curve machining, I believe. Yes, that was a 3-axis curve machining we did. And then finally a 5-axis swarf machining to the outside like that. And then to machine that fillet, we did a between two curves machining there to machine that. It's just pretty nice. Actually, let me run that. I don't want to spend too much time simulating it. Okay, swarf machining to end. So there you go. Yeah, 5-axis between two curves. As you can see, this was, let me turn that back on. This was done using 3-axis mode, and you can see the scallops that are being left. And you really have to control the scallops there when you're doing 3-axis mode, but look at the kind of finish that you're getting in 5-axis. Yeah, you do see some differences here as well, but you can clean that up using a corner radius mill. But the finish here is really, really nice. So that's the advantage of using 5-axis machines, like Don pointed out. Okay, then I want to quickly go through some of the other methods. I want to show you an example of a rotor. This is an interesting case because the way you would, locate this part would be, this would be a rotary table. The table is actually rotating about the x-axis, and then you probably would have a head configuration for the other angle, and also the 3-axis. So I want to show you how we machined it. We did a swarf machining there to machine that wall. We went around that using a swarf machining operation. And then we did a between two curves machining here to get into that channel. And then we did a curve projection machining using a ball of the same radius as that fillet. We just drove that fillet and machined that off. And then the same thing on this side. And then finally, to machine the top, we machined that. And the nice part about the whole thing is we also used all of these 4 operations, and then added, since this is a very symmetric part, we did a rotary instance operation. For those of you who watched the previous webinar, we have this rotary instance operation that can allow us to give us a whole set of the same, basically rotate those operations as a set, and give us a whole bunch of different operations to machine the entire part. It's going to take some time to simulate it, so I'm not going to do that. I'm going to show you. So this is a good example where you're machining using a head table or a table head configuration. And then the next part I'm going to show you is an example where it could be a head table or a table head, necessarily a table. It can also be a head, but I wouldn't do it on a head because the turbine is sitting on a table. I would see it as sitting on a Z-axis table, and then you're machining with either a head, the tool on the head swiveling about maybe the X or Y, or even have two tables. Again, as I mentioned, we did a horizontal roughing, and then we also used 5-axis. This is a surface normal machining. We selected that surface, created a surface normal, very similar to the parallel machining in 3-axis mode. And then we used a Swarf machining for the walls here. As you can see, there's a twisted wall, and the cutter cuts using the side of the cutter and checks to the bottom surface. Same thing on the other side. And then finally the top here. And then very similar, we did a rotary instancing to get the entire set. Okay, we're running out of time, so I'm going to show you the last example, which is our mesh example. Okay, this is the mesh that we got from a customer. They had no idea how to machine it, so we actually helped them machine this. So this was quite challenging because, as you can see, the way they had scanned it, this is a scanned part. And you can see there's a lot of holes in this. How do we machine this? And they wanted to do it on a 5-axis machine. So the way we did this is using control geometry, obviously, the power of the control geometry in 5-axis. What we did was we created, I'll show you the different surfaces very quickly that we had to create. So we created, used the power of Rhino to create that drape surface. So we did a drape surface. It's basically essentially created a closed surface, and that was the drape. And then I'm going to hide that. And then using our mesh module, we actually offset that surface, created a mesh, and then we offset that mesh, and then came up with these. Let me hide that one. As you can see, that's the offset mesh that we came up with. And then we created section curves on that offset mesh. Once we did that, we are able to create a surface. The reason we need a surface is obviously to drive the cutter in 5-axis mode. We created that surface using those section curves that we created. Once we had that surface, and it's got to be underneath because we are actually positioning on top. So we did a horizontal roughing on the side, horizontal roughing, and then used that surface, the drive surface, to actually position to the check geometry. So this is how we machined the sides of this. And we had capped the holes. The nice thing about that, we had also capped the holes at the same time. Once we created that surface, we had capped it pretty nicely, so we were able to actually machine it. And then we created section curves going in the other direction to create that surface and to machine the top, actually. So,
Joe, we did have a question regarding the surface that you created for this mesh. There's a little confusion on what actually that surface is doing and why you need it, obviously.
Okay, yeah. So we talked about the control geometry briefly in the Toolpath method that I showed. So we need the surface to derive the surface normals on the cut pattern. So that gives us the cut pattern to position the cutter along. So that surface is used to define the surface normals as well as cut patterns. Okay, let me, and that's the surface that we use. As you can see, that's the surface normal. We slice that surface to define the surface normal. I'll take off the Gout check geometry. And we use the mesh as the Gout check geometry. So that basically, in effect, allows us to write the mesh geometry. So I'll do that. I'll regenerate that. You might get a better idea. So that's, if I didn't have this mesh at all, oops. I was taking up a lot of resources. Okay, there you go. That's a pretty heavy mesh, so. Okay, it finished. There's your surface. So if I didn't have this mesh, let's say, and I use that surface, that's the toolpath you're going to get. So basically, that's what we use. This is the cut pattern. As you can see, these are parallel planes that define the cut pattern. And not only the cut pattern, we can actually also, I'll show you another option to show you the tool axis normals. There's an option where you can actually display the tool axis. So this actually displays the tool axes. I don't know whether you can see it, but those little lines, those define the tool axis vectors as you're machining it. This is how the tool is going to be positioning. So that's what the surface is doing. It's giving us not only the cut pattern or the cut trajectory for the tool to be, to follow, but also the tool axis normals. I hope that's clear. I think I'll turn it off just to show. Okay. And that you can turn on in the toolpath display, as I just mentioned, as just showed you. Okay, we're almost at the end. I want to quickly show you the machine tool simulation, which is a pretty nice thing that we had set up with. So one of the things that when I talked about the machine tool, I talked about the manual definition of your machine tool. But we also have something, we can also load machine tools from external definitions. And this is what we have, a whole bunch of tools that we ship with the product. And this particular one that we had set up, and then we also can display all the different axes on the machine. Let me run the simulation on this and turn on the machine tool. And you can see the actual machine tool actually working. Oops, sorry about that. That's the entire machine tool. You can see that working. So the product ships with about 25 to 30 machine tools that are commonly available, and these are all 5-axis machine tools. And if you have a specific machine tool that you're interested in, we can actually work with you and set it up. It's not an easy thing to do, but if you're interested, it's a service that we offer. We can help set that up. Right now, some of the limitations of this machine tool simulation is it does not do gout checking. So if your head is hitting another part or another portion of the machine, we do not detect it. So this is not a complete machine tool simulation product. This is more of a visual aid for you, so you can see if there's any collisions or anything like that, purely visually. We don't do this mathematically and tell you that there's collisions. Those are some things that are in our plans, but we don't really want to compete with the big guys who do these machine tool simulation, complete machine tool environment on a computer. We don't want to be there. We just want to use this as a visual aid for you. Okay, on that note, I think we're almost at the end. Let me open it up for questions.
Joe, we had a quick question. Just
Okay.
if we had a moment just to explain the difference between indexed and continuous machining and 5-axis. We kind of glanced over the indexed part,
Okay.
but what the difference is basically.
Okay. Let me go back to Rhino. Okay. Let me stop that. Let me bring up my maybe a little simple part here. So bring this control geometry. Okay, so if you look at this toolpath method, this is a continuous toolpath 5-axis method. So which I will run the simulation and you will see, as you can see, the tool is actually rotating, and not only is it moving in X, Y, and Z, but it's also rotating in multiple axes. It's actually rotating in 2 different axes. And that's why we call that. So there are 5 degrees of freedom here for the tool as it's machining. So now X, Y, Z, the 3 linear axes, as well as the 2 angles. So rotation about either the, depending on your machine tool, about the X or the Y or the Z axis, the principal axis. So that's why we call this continuous 5-axis machining. In index machining, what we are doing is different. We are actually locking a particular axis. We are rotating the tool axis. Let's say we're doing an index machining. We're coming in from this direction. And we're actually locking that tool axis in that position and orientation, not position, just that orientation. And then machining in 3-axis mode. So that is what index machining is, as opposed to continuously varying to toolpath method and 5-axis. Hope that makes sense. All right, Don.
Yep, it looks like we come to the end of the time for this particular webinar. And again, if you have any questions that we didn't cover, or if you think of a question afterwards, please do give us a ring or email us, and we'll get those questions answered for you pronto. And again, this video, the webinar was recorded, and we'll send you a link to watch that in a day or so after we get it cleaned up. Goodbye, everyone, and thanks for joining us. Take care.
Thank you.